little bit on, started with working on biodiesel area, how to produce biodiesel more cost effectively, and use the reduce the water usage for biodiesel production, so especially water washing. And so we try to work in the solid acid catalyst, which can do the esterification, trans-esterification. We're still working in that area. So that's one area we are quite heavily involved. The other area is the glycerol utilization. As you know, it's about 10% byproduct. It's glycerol from biodiesel production facility. So take the glycerol. Mostly the glycerol has also some catalyst and may have some maybe monodiglyceride, may have water. So how do you take this material and then convert it to a useful product? So again, through catalysis, working to convert that to some kind of chemicals that are traditionally produced from petroleum sources. The other work we do is take the waste biomass and use supercritical water to degrade that biomass to fermentable sugar or produce hydrogen. So that's another area. The third area is take the waste biomass and then pyrolyze it, make a liquid. And there are 3-4 companies in Canada which are really good at producing oil from waste biomass. So typically what is done, you take biomass and then put through a fluid bed system at roughly 500 degrees Celsius for a few seconds. And instead of producing a lot of gas, it produces oil. And we call that bio oil. So if you do a material balance, you put say 100 grams of or 100 kilograms of biomass into this reactor, you will get about 70 kilograms of bio oil, which will have of course lots of water that is originally present in biomass, and the rest would be we get char, roughly 15% char, and we call it a biochar, and the other one is just the gas. And the gas will have a medium BTU value, has some hydrocarbons, has some CO2, and some hydrogen. And so that's also a useful gas. You can burn it as well for this pyrolysis work. And the oil that we produce, we traditionally remove the water from it because water has no use in oil, and then either gasify it or treat with hydrogen, so you can produce a high quality diesel fuel. That is kind of direction we are going. And the other work is on the biochar activation to produce high quality activated carbon. As you know, the biochar, if you produce from biomass, has very little surface area and a lot of inorganic stuff in there. And then you activate with the steam, for example. So the surface area can change from 10 square meter to maybe you can go up to 500, 700 square meter. We have ways to go to 1500 square meter per gram. And then that char, once you convert it to activated carbon, you can sell it for maybe $2 a pound. So it's very, very useful byproduct from this waste biomass. And there is also ways to condition the biochar and then use as a fertilizer or supplement. You can adsorb say ammonia, for example, and then it slowly release into soil. And so it basically goes into the soil. At the same time, it adds a value to the agriculture industry. So that's another area we are working on. So what we have in this lab here, this is mostly the instrumentation lab, where we take any catalyst that we use for this upgrading of biomass or upgrading of oil or upgrading of glycerol, things like that. So we have instrumentation lab where you characterize all these solid materials and also look at the mono, di, triglyceride, glycerol measurements. So we have a couple of HPLC. And then the main reaction lab, we have got a number of gasification unit where we can take the temperature to say 1,000 degrees C, and then gasify a material to produce a gas or tar, things like that. And we have some GC to do the analysis. As you know, when you get a liquid or a gas, you have to analyze. People are going to ask you not only how much you produce, they will ask you what is the composition of this material, right? So you need to know that. So we have got GCs. And then this lab here, this is a high pressure, high temperature lab called the Applied Energy Research Lab. And that one has reactors which can go up to 450 degrees Celsius. It's a continuous system, quite a few of them. And then the other one is we also put hydrogen into the system. So this is an explosion-proof lab, and the wall is a fire retardant, and also we have got a roof that can go if we have a fire in. So it's a very good lab to do work with hydrogen, with the flammable liquid and flammable gas. And when you work in such environment, you have to have safety as a #1 priority. So we have got the detectors for H2S, CO, and hydrogen, etc. And also in the lab there will be always more than one person working, so that there's a backup. So nobody is allowed to work alone, especially off hours or weekends. We have more or less people during office hours, but after hours people have to work in the groups. So before we go in, are there any questions you want to ask me? Or it's all clear? Okay. And one more thing I forgot to mention, we also work in the gas to liquid area. So it produces a high quality gas, we call it syngas. And that syngas you can put through a catalyst bed and make ethanol, make gasoline, make diesel fuel. So that's another area we are working for last 5-6 years. So these are kind of what we're trying to do. So let's go to the lab, and then I'll show you a few equipment. And then if you have any questions, then we can look at it. How is the class going? My students' class, so far so good. So in this lab we have surface area measurement equipment. So what that means, if you take fine powder particles or the small particles, you want to measure the surface area. You know why you do that? If you want to use that for catalyst, for example, so the surface area is a very important parameter for any chemical reaction, especially using solids. So we have a surface area measuring device here and another there. So there are two of them. So if you have sometimes any solid you want to know the surface area, you can bring it. It's all automated, so you can measure that for you. And like you can have 1 gram particle, the surface area can be 500 square meter per gram. So that is maybe same as surface area in a football field. So it's a very large surface area. And also if you take say carbon or alumina and you want to measure the surface area, it's roughly 200 square meter per gram. But you can also put metals. For example, if you go to a petroleum refinery and then you see they are doing the reforming and then put platinum on alumina, so produce hydrogen from methane. You know petroleum refineries use a lot of hydrogen, right? And then hydrogen is produced from methane. So you take catalyst bed and then you put your methane and then you put your water or steam, so you produce that the hydrogen. So if you put platinum on platinum, you know, is very expensive. So you put in on alumina, so that the fuel disperse. So you can also measure the dispersion or the distribution of alumina particles on alumina. So you can also measure that with these two equipment. Any questions on this? If you want to give some samples, sometimes you can look at the surface area. And then we have that one is called the temperature program, reduction, oxidation, reduction in heat. What that does is, if you have got a solid substance, you want to know if it's acidic or basic. For liquid, you know, you can do titration, right? But for a solid, so we can do the solid titration and see how much acidic the material is or basic the material is. So we can study there. And we also have a thermal analyzer where Professor Reaney is there in that corner. So that surface area, TGA, thermogravimetric analyzer, what it does is, it will take a material and then subject to high temperature, over 900 degrees centigrade. Then you will see that what temperature is getting, what temperature the mass is going down, so it's producing gas. So you can get the thermal behavior of the particle through that method. So it's a very, very useful tool. And we have got FTIR. If you take a solid material and then you want to look at the functional group, OH group, CO group, you can analyze through that. So that's also very useful. And we have also a equipment there. It's a differential scanning calorimeter, where you can take the temperature down and look at the age change that you have in the liquid. So some of this equipment you may have also seen Dr. Martin's Reaney's lab, but there are some also here that may be useful. And also we have some GC, as you see, for liquid and gas analysis. Okay, when you produce from biomass, you get a liquid and gas. You want to know that. You want to know the composition. You want to control the composition through your reaction. And we have a couple of HPLC there to look at the mononitride, glyceride, etc. So that's what we have here. Any questions so far? What we discussed?
Your thermogravimetric analyzer, can you do that under a inert atmosphere or vacuum?
Actually, it's mostly done at the inert atmosphere.
Inert?
Yeah, with at atmospheric pressure. Vacuum, I don't think we can handle in that one.
Yeah.
In this one, it's mostly do a reaction of solid with either oxygen or maybe just inert atmosphere. You can do the gasification, or you can just do just thermal pyrolysis. And then what it does is just records the change in mass as a function of temperature, and and then you can also measure the heat of reaction as well from that issue. Any questions so far? So let's go to this lab here. So this lab here is that area. Okay, this is our main reaction lab, and what we have here is we have a number of let's go to a little bit. So this area there is more for making catalyst. So we have a lot of different chemicals, so we can make catalyst that we use for either gas to liquid technology or conversion of bio-oil to syngas or bio-oil to value-added chemicals. So we use those two branches. And you see those reactors. I'll show you one here. This is one reactor. This is about 300 cc reactor, and you can put maybe pressurized. You can see you can go to 1500, 2000 psi pressure, and temperature you can go to maybe 350 to 400 degrees C, and then you can do gas, liquid, solid reaction. For example, if you want to convert glycerol to another chemical, you take glycerol and then you put your catalyst, and then it can convert glycerol to some other chemicals at certain temperature, certain pressure. And if you want another gas or liquid, you can also put in there as well. So this is a very versatile setup, and it also has a safety valve. So these are the safety valves. So what happens is, if you pressurize too much, then the safety valve is going to go. So it should be away from you. So you don't want to be pressing the safety valve. That's a problem. And so you can see there's a number of systems here, right? so people can, 4 or 5 people can work at the same time. The tar to maybe some hydrocarbons or maybe hydrogen or CO, things like that. So you can do different things if you have two systems. One is for gasification, the other one is for catalytic conversion. So we have that. So when you put the biomass, you can dry it in the oven or you can dry it here. Then you know how much dry biomass you are taking. Then you measure the composition of the gas. So you can do the composition and you know the total volume. Then you can do the mass balance. How much of that biomass has gone to gas? How much is in the tar? And how much is back in as a solid within the system? So for any work you do, you always have to have a mass balance. How much you are putting in, how much you are getting out, and if there is any loss in the system. And when you do the research also, you have to do same work 2-3 times to see are you able to reproduce your work. It's very, very important. If you are not able to reproduce your work, then your work has not much meaning. So you have to be careful. So this lab is, we have got a working space. Basically when people work in the lab, they want to write a report or browse through the internet or whatever they want to do. So they do that. We also have a small fluidized bed system there. So the fluidized bed system is produce small amount of liquid. So it's not really a large unit. You can produce maybe 5-10 cc of liquid. But what we do is we basically get the liquid from the company that produce large amount of bio oil, and then we process that in this laboratory. Is that clear? We have done also some work with the activated carbon. I told you that you produce from pyrolysis. You can take the oil, take the char, make activated carbon, and we have done some work on injecting mercury in carbon and then taking the mercury out. So mostly from the coal plant, when you burn coal to produce power, you produce a lot of CO2, a lot of mercury, and a lot of oxides of nitrogen, etc. So the idea is to remove the pollutants before it can go to the air, to the atmosphere. So we are able to. We have also another machine here. You want to come here? You have a key for this? I didn't bring my key. So we have got a X-ray diffraction equipment here. So the XRD, if you take a biomass, you can look at the crystallize the structure of the biomass, and also look at the different phases of the biomass, and also for any solid. If you bring a carbon or you bring any solid chemical, we can identify what the chemical is, what the solid is, and biomass has different components, cellulose, hemicellulose, and lignin. You can also look at the crystalline structure of biomass through this equipment. These are newly installed equipment, and so you certainly can look at using it. If you have been part of your research.
What you mean XRD?
X-ray diffraction.
X-ray
diffraction, yeah. Sorry about that. I didn't bring my key, but if you want to some another time take a picture, it's okay. Yeah. Sounds good. Any questions about this particular lab? I also mentioned that we have those racks that we make catalysts, and if you want to do some work where you require few more, we have a couple of few more here also to make catalysts.
I got a question for the students. How many people know what fluidized bed means? You should ask Dr. Dalai what a fluidized bed is if you don't know what it means.
Do you know what a fluidized bed means? So a fluidized bed, so fluidized bed, what happens is if you take some liquid or solid, you want to react it with say another liquid or gas. So you basically fluidize particles, so which bring heat into this your reacting or your feed mass, and then transfer the heat into it, and then produce that liquid or gas from it. So it's a very very effective way of doing the reaction. And why you want to use the complex fluidized bed? Because if you are using the say catalyst particles, those particles are basically coated with your product you produce in the bed, and then you can take the particles continuously out of the bed, and then you gasify the carbon if it's if it is deactivating the material, and then put it back into the bed. So you have got a fluidized bed, and then when you do the reaction, and then you take the solids that are responsible to transfer the heat, and then take it to a regenerator and bring it back again. So it's a continuous process. So the fluid bed, fluidized reactor, and then the regenerator kind of are integrated. Most of the refineries use that system because the catalysts are often very expensive, and then you deactivate very quickly. So you can put it back into another system, regenerate, and put it back into this. So what you saw is you saw a series of So this particular lab is, as I said, it's a high pressure, high temperature facility, and so you can see we have the reactors that are housed in the fume mode because they consume a lot of hydrogen for reaction. So if you take say vegetable oil, right? You take a vegetable oil, and then you put a catalyst in vegetable oil, and then you put hydrogen. The idea is to remove the oxygen that is present in the oil, so that you only have a hydrogen and carbon left in the product. So that is more like a diesel fuel. Okay. So all the reactors are designed so you have a pump, then you can pump the liquid into the system, and then bring the hydrogen. You see the lines on the top there that are dropping down to each unit. So there's a closet there which houses the reacting gas. So you can bring the gas and bring into the system, and then do the reaction and collect the liquid on a continuous basis. And we also have a couple of analyzer here. One, this is called petro analyzer, so it can give the aromatics, napkins, etc. You can analyze it here. And we have a GCMS there as well, so you can analyze the other liquid and gas that is produced from the system. So so I think that is and these are all continuous systems. So the one you saw in the other lab, they are more like pads, semi-pad system. So here is a continuous system. Continuously the liquid in the system, and then they have the temperature controller, flow controller, and pressure controller. So you can control the temperature. You know what temperature you are putting in, what pressure you are putting in, what flow of liquid and gas you are putting in. So we have these are temperature controllers, and we also have a mass flow controller. So the small ones are mass flow controllers, and also have a back pressure regulator which controls the pressure in the reactor. And all these reactors are designed by the students. So when the students come in to do their masters or PhD, they can design this system for themselves, and then do the work. So most of them are designed, and we have some actually outside here, and they're all connected to the GCMS. And we have got the pour point and cloud point equipment here, which can measure the cloud and pour point of liquid that is produced we have also a ultrasonic equipment, ultrasonic capability. So what ultrasonic capability does is find that and then called bubbles, and the bubbles which are a lot of energy. Bubble flash, then it transfers the energy to the liquid, and you produce. You can do the reaction very quickly to that particular system. When you want to work with the biomass, you want to make little particles. So we have got also a particle size analyzer in another lab, and we can make large particles with those two pelletizers there. And when you transfer some reacting material from one system to the other, then it's a glove box, so you can use that. So in this particular lab, you can do any gas, liquid, solid reaction at different temperature or pressure conditions. So it could be glycerol, could be bio oil, could be vegetable oil, and we have also done some work with the activated carbon produced from biomass and injecting hydrogen sulfide. So hydrogen sulfide splits into sulfur and water. So you can produce also sulfur and water. So you take H2S and inject a little bit of oxygen, and then that oxygen takes the hydrogen out to produce water, and the sulfur stays in the bed. So the activated carbon that is produced from biomass is also very, very useful to capture, not only capture the organic pollutants from chemical plants, but also very useful to capture the sulfur from. Go up to 300, 400 degrees Celsius in these reactors, and pressure can be up to 1500 psi, and then the flow rate, you can change the flow rate. You can go very high flow rate, you can put gases, maybe we can use 3 liters for 3 liters or 5 liters per hour of gas we put in, or liquid you put in, 5 liters, and then gas also about 600 times that. So you can put a lot of gas to the unit if you want. So we have, it's very versatile, you can do a lot of things. And the reactor itself is made of inconel, so that it does not corrode very quickly. So corrosion is an issue when you use some liquid and gas for reaction. You have any question? No, you? No? What about you? Huh?
No.
No question? What about you? And you, sir? Everything is clear? What about you? Is it okay?
Yep.
So what is the most interesting part so far? What you saw? What is the most interesting part? Or maybe nothing is interesting. Which one is more interesting for you? Not equipment. Which one do you think is most useful? Huh? So do you want to give this other example? Yeah. Okay. So it takes about, if you want to, for example, use the facility, probably take you about a month to get trained. This don't take too long because it's mostly automated. So you have to work with somebody, and then that person will transfer all the knowledge. Then you can handle it on your own. Sounds good? Should I go to, what about you, sir? Is everything clear? Yeah? Everything?
You just mentioned you inject the hydrogen to the vegetable oil.
Yes.
And
And
with
remove water.
Remove water.
Yeah.
So it's kind of carbohydrate to make
Hydrocarbon, like a diesel fuel. When you look at the diesel fuel that you put in a diesel vehicle, it does not have anything except hydrogen and carbon. So the idea is to create hydrogen and carbon combination.
Where the hydrogen.
This pilot plant can generate activated carbon from a biochar. Okay, So when you do the first pyrolysis, you produce char, and you can take the char and put in that. That is our reactor. So you can hold about 500 kilograms of char, and we have a boiler here. To make it more smaller. That is from there, and it's all built in here. And there is another unit here. This is a small, it's a baby one, and that's a pile. So this is exactly same as that one. So it can hold 20 grams. That can hold 5 kilograms. So it's scaled up from this one. Okay. And Regan, do you have a minute to talk to them what you are doing? Okay, do you want to listen to him? Maybe a couple of minutes.
Powdered gold. Feed it in to the heated section here. It's up to 800 degrees C. And then it gasifies because there's not enough oxygen for it to burn. So we produce hydrogen, carbon monoxide, all kinds of gases, and then we measure those. So that's what our experiments are, all the different gases we can create. This is a really small gasifier. Come over here. There's another one.
Oh my god.
So this is another gasifier, just much bigger. There's a system for feeding the material into the bottom, and then it goes right up and out the roof here.
So loop here to just connect this loop and then can collect some of the gas.
Right, we collect some to sample and to test.
This line, this one?
And then the rest, yeah, that's the line there.
Okay.
And then the rest go out, just out a chimney out to the roof.
Okay.
It's a fluidized bed gasifier. So in the bottom of it, there's actually sand with air bubbling through it. So it's moving and flowing, and into that 800-degree sand, we inject the feed, and it reacts very quickly.
Compared with this gas tank and here, this one, what's the difference capability?
Between the little one and the big one? Well, this one's about 10 times larger, but it takes much longer